So what I'm showing you is a simulation of the coronavirus pandemic based on something called an SIR model. SIR stands for susceptible, infected, and removed. Let me walk you through the details. The green dots in the graph below represent the susceptible population. The red one represents the infected population, and the gray one represents the removed population. It means either they have recovered or are dead, unfortunately. You can see the statistics above the graph. The R value, others are simple. The R value is called the effective reproductive number. It's the number of secondary infection caused by one primary infection. Basically, when it's greater than 1, that's when the disease is called an epidemic. When it's lower than 1, it means the disease is on the decline, and when it's equal to 1, it's called an endemic. On the top right corner, there are some hyperparameters. So 1 day in the simulation is equal to 0.1 second. So the way the simulation works is that each entity has something called an infection radius. It's basically a circle in area around an entity. When another entity enters that area and spends 1 day inside it, it has some probability of being infected. That is written on the top right corner. The box at the bottom right corner is the quarantine, and yeah, there is a quarantine probability too. So after some days, an entity has some probability of being quarantined. We will control all these parameters later. So let's start with a vanilla simulation. In this kind of simulation, when no precautions are taken, it means the infection probability is all-time high, and the infection radius is also all-time high because no one is taking any precautions or any social distancing, and there is no quarantine. Let's run the simulation and see what happens. You can see that almost immediately the entire population gets sick, which is terrible because that's not something we want. We don't want all the population to get sick. Now let's attribute some factors. Let's say that people lower their interaction with each other, so then they don't travel a lot, they don't go out of home, and that kind of stuff, but they still don't take precautions like wear mask and use sanitizer and use gloves. They don't do that things yet. Now if I'm in the simulation, you can see that almost all of the population still gets infected. The graph is flattened out a little bit, but almost entire population still gets infected. Now let's lower the infection probability. So this can mean more social distancing and more precautions like use of sanitizers, masks and gloves, no face touching, no handshaking, kissing or hugging and that kind of stuff. So if we decrease that, let me decrease that. As you can see that the graph is flattened out even more, but the total infected is still 287 out of 300, which is not good. It's definitely not good. It definitely flattens out the graph, and there are some advantages of the graph flattening out. This way the medical system won't get overwhelmed because there's gonna be some line over here. It depends on the countries. For some countries, it's gonna be here. For some, it's gonna be here. For some, it's gonna be very low, where they are not very developed. But there is gonna be some point at which the health system overwhelms, and the health system is overwhelmed when there is a spike in the graph. So the flattening out of the graph definitely helps, but the total number of infected is still all-time high. Now let's do something else. Let's decrease the social interactions further so that people don't go out a lot. So let's decrease the infection probability and the infection radius. So what it means in real life is that now people are very precautious. They don't touch a lot, they don't hug, kiss, and they don't do that a lot. So yeah, now let's run simulation again. You can see the disease kind of contained in this one region, and so when not a lot of people travel, they don't travel a lot, they don't go out a lot, you can see that the disease is contained in one specific region of the population. And when people do, like, I'm gonna increase the social interactions by a factor of 4, and now let's see what happens. So the people are interacting more, but they are precautious, like, still. As you can see that precautions help up to a very big extent. Previously, when the precautions were lower, we had somewhere 287 to 257 to 287 total infected, and now social interactions are pretty high, but we still have the total infected lower, much lower. This just shows the value of precautions using sanitizers, masks, and gloves. It just shows the amount of impact it has on the pandemic. But let's not forget that we saw that pretty long tail. The pandemic lasted for a very long time due to people traveling a lot more. So the traveling is definitely not good, and self-isolation definitely helps, but the precautions matter much more, I would say. Now let's do something interesting. Let's say we have a lot of people, like almost everyone is self-isolated. They don't travel a lot, and but a few people, they still travel a lot. So this can represents houses. One person, one member of the house goes a lot, other remains still at house. Let's see what effect it has. Now let me add something else. So in this simulation, the infection radius, the infection probability is gonna be very high. So the people who travel a lot, they are gonna have a higher probability in infecting other people. So a lot of people at the home are staying still, but one of the house members is traveling a lot and not using any precaution. Let's see what effect that has. Let's test it with something else. Now let's say only 80% of the population remains still, but 20% of the population still moves a lot, and see what happens. You can see a common trend here. The more I increase the number of people who travel, the more the infection spreads. That's kind of the basic pattern. So I think the stay home, stay safe, that is a pretty effective thing to do in these times. And the precautions definitely help. They help a lot. These are the two key takeaways from these simulations. And let me remind you, these are simulation toy models, and I will leave it to the intelligence of the viewer to judge if these entities correctly simulate our society. And now let's test the theory of quarantine. Let's see whether the quarantine helps or not. So I will get everything back to normal, and let's introduce the idea of quarantine, whether quarantining people helps or not. So everyone is gonna have a 70% probability of being quarantined. So the remaining 30% are not quarantined because they are asymptomatic, or they're cheating, or there are no quarantines or something like that. There are no resources or something like that. But for some reason they are not quarantined. Let's see what effect it has. The quarantine is started a little bit time after the infection. You can see that there is a spike, but as soon as the quarantine is enabled, that drops tremendously. It halts the infection right in its path. This proves that the quarantine strategy is extremely useful. Let me modify the factor. Let me decrease the number of people quarantined and the quarantine probability. So less people are quarantined. You can see that the more I decrease the probability of an entity being quarantined, the longer the tail is. That's a common trend. The less people are quarantined, the longer the tail will be, and for the longest time the epidemic, and for a longer time the epidemic will last. There's one more key takeaway, and that is that the quarantine definitely helps. There's one more thing too. We are isolating the cases. That's what the quarantine represents. But a vaccine, but this quarantine theory can also represent a vaccine. Let's say we have made some kind of vaccine or medicine that can cure the coronavirus. Then that is equivalent to separating and isolating those cases